you would see that it's dropped very suddenly. So just to wrap this part up is going over ice tables. I was going to leave it, but I do know you'll most likely be asked a question about ice, so just knowing how it works is important. So the first part is that I is based on concentrations, initial concentrations. So if you're only given moles and the volume, make sure you divide before you go. The other part is when you're looking at your total equation. So let's make something easy like hydrogen plus oxygen to give you water, and then go ahead and balance it. If you were given the concentration of, say, hydrogen or oxygen to start, so you could write that down, whatever, it's not a 0. You can write that down. So say it was like 2, I'm just making this up. Water, if it doesn't tell you otherwise, initially you can assume 0. Then your change is based on your mole ratio. This is where we're going to introduce the variable. Reactants are used up, so you're going to subtract them based on the mole ratio. So minus 2x minus x. Products are being formed, so you add them. Now your equilibrium, this is still your concentration, but to get it, you add what you have above it. So this would be 2 plus negative 2x. So we have that, and we have that. Now equilibrium, because that's what Ka and Kb and Kc represent, that always will be that last column. So the values you get here, so you might have something that allows you to solve for x, you would plug it in. If you knew all those values, then you can go over to your equilibrium formula. If you don't have those values, you're probably going to find them, so you would solve for x using a Ka or a Kb. Or a Kc for that matter. So the last part is just your Ka and Kb formula. They only apply to weak acids and weak bases because if it's strong, they're not in equilibrium. If you're looking at this and you're solving for Ka, you have the rest of this information. So you take your hydronium, square it, divide it by the concentration of your weak acid minus hydronium. That will give you your Ka. Kb is similar. If you are solving for hydronium, then that means you have your Ka. In these cases, you can ignore the hydronium in the bottom and solve that way because it is a weak base or weak acid. You have very little in the product side. The very last thing, I just wanted to go back because I just realized that I did not touch on is when you're looking at your systems over here, endo and exo. Another very, very important one, and I'm not sure why I don't have it on here, is about calorimetry. So if you have calorimetry, you know it's going to be NH equals negative MC delta T. Here, know your 3 assumptions. So being that energy, if it is lost, it's negligible. We always have the specific capacity of water, and there is one more that is escaping me at the moment, but I'm definitely guarantee you have it somewhere when you write it down. Also knowing if it's a neutralization reaction, you add the acid and base together to get the mass of your calorimeter. And if it is bomb calorimetry, the NH part is the same. That negative MC delta T is the same as this part is about the reaction. It's going to be the same here about the reaction. This part is going to be about the water. And then the last part, if it is bomb calorimetry, it means your container is gaining heat, and it's usually because you're using a combustion reaction. So you're going to add on a negative MC delta T to do with the container. Just one more thing to add here. If that is the case, if you're only given one final temperature, you can use that final temperature for the container as well. Okay, I think I have everything now. I hope you find this helpful. If you did, please subscribe. If your tests are coming up, best of luck to you, and I hope it goes really well. Thank you for watching.